In this second part, we're going to see 5 more important physics laws. If you're not done yet, go check the first part. Let's start with the Kepler laws of planetary motion. Kepler published 3 different laws in order to describe the motion of planets around the Sun properly. The first one states that the orbit of a planet is an ellipse, with the Sun at one of the 2 foci. The second one states that a line segment joining a planet and the Sun sweeps out equal areas during equal intervals of time. From the second law, it's possible to understand that when a planet is closer to the Sun, it travels faster. Finally, the last of the 3 laws states that the ratio of the square of an object's orbital period over the cube of the semi-major of its orbit is the same for all objects orbiting the same thing. All these 3 laws are vastly used every day in space and astronomic fields. An important principle for fluid is Bernoulli's principle. It states that an increase in speed of a fluid occurs simultaneously with a decrease in static pressure. So the speed of the fluid is inversely proportional to the static pressure. An application of this principle is the floor of an F1 car, for example. The increase of the velocity of the flow results in a decrease of the pressure, and so it creates a forces point down called downforce. Now let's talk about electromagnetism. Introducing Faraday's law. It's very important in order to predict how a magnetic field will interact with an electric circuit to produce an electromotive force, usually called EMF. This is due to a phenomenon called electromagnetic induction. So what does this law state? It states that the electromotive force around a closed path is equal to the negative of the time rate of change of the magnetic flux enclosed by the path. The electromotive force is indicated with epsilon, meanwhile the magnetic flux with phi. This law is the basis of the operation for transformers, inductors, and a lot of electrical motors. Another fundamental law to always keep in mind is the conservation of energy. Indeed, it states that the total energy of an isolated system remains constant, and so it will be conserved over time. A famous sentence with which it's known is energy can neither be created nor destroyed, rather it can only be transformed or transferred from one form to another. An everyday example can be seen playing pool. The first ball is shot at another stationary ball, and so the energy transfers from the first ball to the second, putting the second one into motion, neglecting the heat due to friction. The first ball loses kinetic energy because the energy has been transferred to the second, and so it will slow down. And finally, the last but not the least law of this video, we're talking about Hooke's law. It states that the force needed to extend or compress a spring by some distance x is directly proportional to the distance. So the formula will be this one. K is a constant, and it represents the stiffness of the spring, and it could change depending on the type of the spring. You can observe that the extension of the spring is proportional to the force applied, so in this case, doubling the mass, the extension of the spring doubles. If you are also interested in Newton's laws, you can check my other video in which I explain Newton's 3 laws with some interesting application. If you like this video, please leave a like and remember to subscribe.